A heartily welcome viewer and welcome to my Tech Talk video. Before starting this Tech Talk, let me introduce myself. My name is Bhuvneshwar Sankranti and I am currently pursuing my undergraduate BTech degree from Institute of Aeronautical Engineering, which is basically located in Dundigal, Hyderabad. And I basically belongs to Computer Science CSC A section, and my roll number is 21951A0527, which you can see on my screen or my PPT. And without without further delay, let's move into our today Tech Talk video. Let's go. In this Tech Talk is regarding the subject linear algebra and calculus, and today Tech Talk topic is by unitary transformation. In this whole Tech Talk video, I am going to cover the over theory of the biunitary transformation and it related topics. Okay, we will move to the further slide. And topic learning outcomes. Name of the topic covered as discussed earlier, biunitary transformations, and topic learning outcomes. The outcomes after completion of this Tech Talk video will be, by the end of, we will going to learn some information and some examples of biunitary transformation. Finally, what are the topics covered in this whole Tech Talk video? Let me divide into first two topics. First slides I am going to cover what is diagonalization and some examples of diagonalizations. In the second part, some theory of biunitary transformations, and at the third, I am going to discuss how diagonalization and biunitary transformations are related and how these two are correlated. And fourth one, practical applications of biunitary transformations, or I am going to discuss some examples about the biunitary transformations. Let's move on to the next slide. Here, introduction. We can simply diagonalize a square matrix which has the model matrix, which means we can get eigenvectors of given matrix, and the model matrix will be symmetric or Hermitian. Then what about the mass matrix which does not have neither symmetric or Hermitian? Here we can use biunitary transformations to get the matrix diagonalizable. The whole idea of this slide is, if for simple diagonal square matrix, it has a model matrix which is asymmetric or Hermitian. If some matrix will be there where there will be no model matrix which has symmetric or Hermitian. For those matrix, we can diagonalize that matrix by using the biunitary transformations. While starting with biunitary transformations, the first question arrives in our mind to start the topic biunitary transformation is matrix diagonalization. First of all, what is meant by matrix diagonalization? In first three slides, I am going to discuss what is matrix diagonalization. These are the pre-requirements to learn the biunitary transformation. So by quick and forward method, I will continue what is by matrix diagonalization. Let A and B are two matrices of order n. Let us take two matrices A and B which has of an order n, which are basically a square matrix. B can be considered similar to A. We can consider B matrix which is similar to A if there exists an invertible matrix, means inverse of matrix P, such that B is equal to P inverse AP. If it satisfies this condition, B is equal to P inverse AP, then we can say that B is similar matrix of A. This is known as matrix similarity transformation. Okay, we will move on to further slide. Diagonalization of a matrix is defined as the process of reducing any matrix A into its diagonal form D. As per this similar transformation, if matrix A is related to D, then D is equal to P inverse AP. As we discussed in the previous slide how A and B are similar transformation, here we are diagonalizing the A matrix. We are diagonalizing the A matrix where P is called as model matrix. See, diagonalization of a matrix is defined as the process of reducing any matrix A into diagonal form D. As per the similar transformations which we did in the previous slide, if the matrix A is related to D, then the matrix C is reduced into diagonal form D. By applying this equation, if you do this equation after getting this D, then this is called the diagonal matrix D, and another matrix P is called the model matrix. Here the P is known as the model matrix. The basically model matrix is nothing but the arrangement of eigenvectors. And here in this slide we are going to discuss about the model matrix. What is a model matrix? It is an n into n matrix, a matrix which is on order of n, that consists of eigenvectors. The basic idea of the model matrix is the filling the eigenvectors in column wise of a square matrix n into n. It is generally used in process of diagonalization and the similarity transformation. The model matrix is, before slide we seen that model matrix P is used in previous slide to diagonalize the A matrix into D. In simpler words, it is the process of taking a square matrix and converting into a special type of matrix called diagonal matrix. So by simply saying, model matrix is nothing but taking a matrix and converting into simple type of matrix called a diagonal matrix. Okay, here we see an example how to convert a given matrix into diagonal matrix. There are total 5 steps involved. I will discuss this step by step. Diagonal matrix, how to convert a matrix into diagonal matrix. Steps involved. Step 1, initialize the diagonal matrix D. First of all, we should initialize the matrix D as lambda 1 0 0 0 lambda 2 0 0 0 lambda 3, where lambda 1 lambda 2 lambda 3 are eigenvalues. First we should initialize the diagonal matrix where lambda 1 and lambda 2 and lambda 3 are eigenvalues, and we should start with in this form, and we should move into step 2. Here the steps 2 arrives. In step 2, find the eigenvalues using the equation below. Here this equation is called an characteristic equation. By using this equation, det of A minus lambda A, where A is given in the problem and the lambda is an lambda constant, eigenvalues, further we will get for the lambda, in further we will get lambda value as an eigenvalues, and I is an identity matrix. Det of A minus lambda I equal to 0. By using this equation, we should find out the eigenvalues. For lambda we will get the eigenvalues, where A is given 3 into 3 square matrix, or 4 into 4 or 5 into, it's our wish, but it should be a square matrix, where A is 3 into 3 or 4 into 4 square matrix, and I should be a matrix of same size. If you take here A as n order, and here I should be the same order of A, and A and I should be the same order, and lambda value at finally we will get are the eigenvalues. Okay, we will discuss step 3. In diagonalization of matrix, step 3 comes here. Compute the corresponding eigenvalues. We should compute the corresponding eigenvalues, where lambda I is the eigenvalue and xi is the corresponding eigenvector. Step 4, create the model matrix P. Now the step 4, we have to create a model matrix where we got x0 and x1 and xn. Before we got xi as an eigenvalues. By using that eigenvalues, we should find out the eigenvectors too. We know that how to convert the eigenvalues. By using eigenvalues, how can we find in eigenvectors? By using that, if suppose lambda 1 is the eigenvalue, by using that we should find out the corresponding eigenvector x1. By getting that, if it is a 3 into 3 matrix, we will get lambda 1, lambda 2 and lambda 3 are the eigenvalues. For those corresponding x1, x2 and x3 should be the corresponding eigenvectors, or x0, x1, x2 will be the corresponding eigenvectors. If it's a 4 into 4 matrix, lambda 1, lambda 2, lambda 3 and lambda 4 will be the eigenvalues, and corresponding x1, x2, x3, x4 will be the corresponding eigenvectors. Here we got eigenvectors. By using that eigenvectors, we should construct a model matrix where x0, x1, x2 and so on xn will be the eigenvectors, and we should construct a model matrix P. Here all eigenvectors till xi are filled column wise in the matrix P. Here all the eigenvectors till xi in column wise is filled in the matrix P. Okay, the final step which we arrive is step 5, fill P. Here we should find the P inverse. As we got P in the previous slide, by using the model matrix by using the x1 values, or the lambda which we made the model matrix by using the eigenvectors. We should similar way we should find the P inverse by using Gauss-Jordan method. We should find the P inverse, and they use the and we should, after finding the P inverse, here we have P inverse and given A in the question, so we should find here D, and so we should find here D by using this equation. And here we see an example problem statement. Assume a 3 into 3 square matrix A having the following values. So let us see the question. The following elements in the matrix are 1 0 minus 1 1 2 1 2 2 3. Then the question is, find the diagonal matrix D of A using the diagonalization of matrix D is equal to P inverse AP. Here it is a solution according to we discussed in the previous slides. It is the step 1, initializing the D. As we discussed earlier, we should initialize D as lambda 1, lambda 2, lambda 3, lambda 1 0 0 0, lambda 2 0 0 0, lambda 3. This is our first step. And further moving to second step, let's find the we should find the eigenvalues. First we should find the eigenvalues, or the lambda, which is known as eigenvalues only. As I discussed, this is by using the det of the characteristic equation, det of A minus lambda I, det of 1 minus lambda, 0 minus 1, 1 2 minus lambda, 1 2 2 3 minus lambda, whole det equal to 0. We should equate it, whole det equal to 0. And by finding the value, we get this det as lambda cube minus 6 lambda square plus 11 lambda minus 6 equal to 0. By further simplifying, we will get lambda minus 1, lambda minus 2, and into lambda minus 3. Here lambda minus 1 into lambda minus 2 into lambda minus 3 equal to 0, where the lambda is equal to 1 comma 2 comma 3, where lambda is nothing but the eigenvalues. Here 1 comma 2 comma 3 are the eigenvalues of the given matrix. As we got here the eigenvalues, first then we should find the eigenvectors to build a model matrix. By using this 1 comma 2 comma 3, I will find the eigenvectors here. Here the step 3, find the eigenvectors x1 x2 x3 corresponding to the eigenvalues lambda equal to 1 comma 2 comma 3. For at lambda equal to 1, a minus of 1 into I x1 is equal to 0. Here 1 minus 1 0 minus 1 1 2 minus 1 1 2 2 3 minus 1 into x1 x2 x3 equal to 0 0 0. For next step we will get 0 0 minus 1 1 1 1 2 2 2 into x1 x2 x3 equal to 0 0 0. On solving, we will get the following equation: x3 is equal to 0, x1 plus x2 is equal to 0, x2 is equal to x minus 1. By solving this, we will add x1 is equal to x1 minus x1 0 into x1, where x1 is equal to 1 comma minus 1 comma 0. Similarly for finding lambda is equal to 2 and lambda is equal to 3, we will get x2 is equal to minus 2 1 2 3. And for x3, for lambda equal to 3, we will get x3 corresponding eigenvector as 1 comma minus 1 comma minus 2. Here we got 3 eigenvectors. For lambda equal to 1, we got 1 minus 1 0. For lambda equal to 2, we got minus 2 1 2. And for lambda equal to 3, x3 is equal to 1 comma minus 2 comma minus 3. Here these are the values of eigenvectors corresponding to the eigenvalues of 1 comma 2 comma 3. Step 5, as we discussed, step 5 is creation of model matrix. Here x1 x2 and x3 are column vectors. Before we got 3 vectors, right, eigenvectors. We should arrange them in the column, not the rows, as shown in the PPT. P is equal to x1 x2 x3 equal to 1 comma minus 1 comma 0, this is the first eigenvector, minus 2 1 2, this is the second eigenvector, 1 minus 1 1 minus 1 minus 2, this is third eigenvector. By arranging this way, we will get the model matrix P. And sixth step, we should find the P inverse. For the equation D is equal to P inverse A into P. For substituting in that, we should find the P inverse. Finding P inverse and putting the values in diagonalization of the matrix D equal to P inverse AP. For putting the P inverse and P, and as we know A in A, So by putting in these three values, you will get the diagonal matrix D. We do step 6 to find out which eigenvalues will replace lambda 1, lambda 2, lambda 3 in the initial diagonal matrix created in step 1. P equal to 1 minus 1 0, minus 2 1 2, 1 minus 1 2. Det of P is equal to, as by finding the det of the P, we will get det as 2. Since det of P is not equal to 0, P is invertible. First I am checking the condition, does the P is invertible or not. As we know that if P is invertible, det of P is not equal to 0. As det of P is not equal to 0, P is an invertible matrix. We know that P inverse is equal to adjoint of A by det A. By using this method also we can find, or otherwise using Gauss-Jordan also we can find the P inverse. P inverse is equal to, we will get P inverse as 1 by 2, 0 minus 2 1, minus 2 minus 2 0, minus 2 minus 2 minus 1. Putting in diagonalization of matrix equation, we will get, as we discussed in the earlier, the equation of the diagonalization of matrix is D equal to P inverse AP. By putting these three values in this equation, we will get D as 1 0 0, 0 2 0, 0 3 0. This is the process how we will find the diagonalization of matrix, and for the given question we got the diagonalization of matrix as 1 0 0, 0 2 0, 0 0 3. And what is unitary transformations? In mathematics, a unitary transformation is a transformation that preserves the inner product of two vectors before the transformation is equal to the inner product after the transformations. The basic idea of the unitary transformation is the core term, the inner product before the transformation and after the transformation should be equal. That's the basic idea of the slide. The formal definition for the unitary transformation. More preciously, a unitary transformation is the isomorphism between two Hilbert spaces. In other words, a unitary transformation is a bijective function. Let us take U, which ranging from h1 gives rise to h2, where h1 and h2 are Hilbert spaces, such that u of x1 comma u of x2 h2 is equal to x1 y1 x comma y h1. Properties of the unitary transformation. A unitary transformation is an isometry, as one can see by setting x is equal to y in this formula. Unitary operator, in this case when h1 and h2 are some spaces, a unitary transformation is an automorphism of that Hilbert spaces, and that is also called as a unitary operator. And coming to the biunitary transformation, the basic definition, biunitary transformation, the important point is that there is no reason for this mass matrix to be diagonal. In fact, generally they are neither symmetric nor Hermitian. We shall now demonstrate that this type of matrices can be diagonalized by this type. We shall now demonstrate this type of matrices can be diagonalized by biunitary transformation. Given MEAB, there exists a unitary matrix SST. For a given MEAB matrix, there exists a unitary matrix SNT such that SMT is equal to MD, where MD is the diagonal with positive eigenvalues. Basically, these points are any matrix M can always written as the product of Hermitian matrix H and unitary matrix V, where M is equal to HV. And the Hermitian matrix H can be diagonalized by some unitary matrix. Here the proof proceeds as follows. M into M dash is Hermitian and positive, where M is an Hermitian and M dash is the positive. It can be diagonalized by a unitary matrix S. S dash into M dash S is equal to MD square, with MD square is equal to M1 square, M1 square, M2 square, M3 square are the diagonal elements of the matrix, of a square matrix. This matrix S is unique up to the diagonal phase matrix, such that in equation 1 1 1 is to 1 1 1 holds, then SF dash into M dash into whole SF is equal to MD square, with F is equal to e power xi 2 e power xi 3 as diagonal elements of the square matrix F. This phase degree, this is the phase, this xi is known as phase. This phase degree of freedom will be studied in more detail when we take up the equation of CP violating gauge coupling. There we can use it to ensure that the eigenvalues of M in are positive. For the further side, we get MD equal to M1, M2 and M3 as the diagonal matrix of MD, where Mi means M1, M2, M3, and if you take 4 into 4 matrix, 5 into 5 matrix, we will get as M1, M2, M3, M4, M4 as the diagonal matrix, where Mi is greater than should be greater than 0. Define a Hermitian matrix H by using these all formulas. We will define a Hermitian matrix H is equal to S into MD S slash. Then we can show that V defined by V is equal to H inverse M and V dash is equal to M dash H inverse is a unitary matrix because of equation 11.1 and 11.114. V dash is equal to H inverse M dash H inverse is equal to H inverse S M dash square H inverse M square equal to H inverse whole of S MD S dash into whole of S MD S dash into H inverse is equal to H inverse into H inverse is equal to 1. By proving this, we can do the diagonalization of matrix which does not have an Hermitian and the square diagonal by using the biunitary transformations. Fermion family representation. From the definition of H and V, equation 11.114 and 115, we have S dash HS is equal to S dash M, V dash S is equal to MD, S dash MT is equal to MD, where T is equal to V dash, T is similar to V dash S is a unitary. This is promised result. Thus the relation between gauge Young states and the mass Young states follow. This equations we will get in Xi L M Xi L R is equal to Xi L S into S dash MT T Xi R, where Xi L and MD Xi R with VL is equal to S Xi L, V dash Xi R dash is equal to T Xi R. And this is the last slide of my video, or we can call as the TechTalk video. Thank you viewers, and this is the my TechTalk video. And once again I have to thank you for spending your most valuable time here in my TechTalk video. Thank you.